Alright, Calc. I have a sick kiddo at home today, so I am recording this video for you. I'm kind of coming down with a bug too, or have a bug, or had a bug. So hopefully my coughing doesn't disrupt this video too much. But um, I'm going to go ahead and give you guys notes for section 2.2, which is 4 pages long, but most of it is just like showing you graphs of things. So it's not too terribly hard. What you will need to do is on my front table, it's like the furthest stack to the left, your left or my right. There will be section 2.2 notes for calc. Grab that, pass those out so that you can fill these note sheets in as you're watching this video. So if you're in the library, you might have to run into my room, or I don't know if it's locked, steal a key from Angie or somebody to get in and get those notes. So while you're waiting for those notes, you can go ahead and pause this video. And then as soon as you have those note sheets, hit resume and I will go through them. So, all right, I'm going to go ahead and start. So in section 2.1, we talked about quadratic functions, and this is higher degree polynomial functions. So x to the third, x to the fourth, x to the fifth, etc. And a lot of the same qualities happen with x squared as they do with higher power functions, like the transformations, left down, upright, reflect across x-axis, that type of thing. Those are all consistent, whichever function you're talking about. But one of the important things to note for polynomial functions is that they are like rounded. They're curves and they have smooth edges. They don't have any jumps or skips in them, and then they don't come to a sharp halt. So this would be like an absolute value function. This would be like a piecewise function, but these two, this first excuse me, this first and this third graph are graphs of polynomial functions. So even functions are going to be like very similar to the graphs of x squared. So like x to the fourth power, x to the sixth power, etc. Odd functions will be like x to the third. So those would be like x to the third, x to the fifth, etc. I don't know, you might also remember that when we did even functions, there was a test for even functions. Even means that it has y-axis symmetry, so I'm going to write that down here. There we go. Even is y-axis symmetry. I think you guys had that on your last test. Y-axis symmetry, and odd is origin symmetry. So the test for that was that if you could plug in negative x comma y into the function and it turned out to be the same, then it was an even function. It was an odd function if you plugged in negative x and negative y and you got the same function out as what you started with. So those are just kind of some quick tests, but most of the time it's going to be like x squared, x to the fourth, x to the sixth, that type of thing, or x to the third, x to the fifth, x to the seventh, etc. for odd functions. Okay. Now I have kind of been lying to you over the years that like x to the fifth power is something that has like really lots of bumps in it. And it technically does. Like x to the fifth power would have a lot of bumps in it if it's like x to the fifth power plus 4x to the fourth plus 7x to the third, blah, 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 and it has all that stuff behind it. But if it is just x to the third power, like the parent function x to the fifth power, if it's just that, that guy, he's going to look really similar to x to the third power, but he's going to be really flat in the middle, like really super flat. If he is like x to the fourth power, I have kind of been lying to you as well there, that it is not a w. X to the fourth power by itself is not a w. X to the fourth power plus some x cubed plus some x squared plus some x plus blah, 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 that is going to be a w. But this one, if it's just x to the fourth power, will look kind of like a flat tire, right? So he'll come down like a quadratic function and he'll be really flat in the middle. That's what x to the fourth power will look like. So those parent functions are just going to be kind of different than what you maybe have seen before. But sketching the graph of each function, this is the answer to those. So negative x to the fifth power, if this is what x to the fifth power looks like to start with, negative, this is going to be a reflection over the x-axis. And that's the same as what you've been used to over x, just flips him down. And then this guy, the plus 1, since he's in parentheses, is going to move him 1 unit to the left. 1 unit left. Because plus 1 actually means left 1, so instead of him being at 0, 0, he's going to be at negative 1, 0. Okay, so pretty basic to start with. Oh gosh, now I have to figure out how to get my, oh, there we go. Second page. Second page. So the leading coefficient test is basically saying that if it's negative, it's going to go downhill from left to right, and if it's positive, it's going to go uphill. So kind of like when we have x to the third power. He kind of looks like this, right? And negative x to the third power is going to look the same, but going downhill, right? So that's the leading coefficient test. It kind of tells you what direction he's going and what he's going to look like. So if it's, let's see, when n is odd, when n is even. Okay, so when n is odd, in addition to him being positive, negative, when n is odd, like x to the third power or x to the fifth power, they're going to end up in opposite directions. If he's positive, he's going to go uphill. If he's negative, he's going to go downhill from left to right. Now, that doesn't mean that his bumps won't make him go back up, but his end behavior will be positive, negative. When n is even, so like x to the fourth power or x to the sixth power or x squared or anything like that, if he's positive and even, then he's going to go up and up. If he's negative and even, he's going to go down and down. So this is positive, even. This is negative, even. This is positive and odd. And this is negative and odd. Okay. So those are just kind of the patterns of what he looks like. So describe the right hand and left hand behaviors of each. We're looking at the parent function x to the third power, and he's negative. So what's going to happen to my graph is, he might be bumpy or whatever, but in general, he's going to do this direction, right? This is kind of, in general, what he's going to look like, okay? So we're going to talk about our end behavior, left and right hand behavior, and we always started out by saying, as x approaches infinity, y approaches something, and then as x approaches negative infinity, y is approaching something. So each one of those is going to be set up exactly like this, okay? And then we have to determine by this parent function or this function what he's doing. So as x approaches infinity, x is the coordinate that goes left and right. So as x goes toward infinity would be the right direction. So this is basically saying as your x is going to the right, as it's going this way, he's going downhill, right? As he's going to the right, he's going downhill. So the y coordinates are going down and the y's are approaching negative infinity. Okay, then as x goes toward negative infinity, that's the left direction. So as my x's are going this way, what's happening? Well, he's going uphill, which means that the y's are going toward positive infinity. Okay, so let's do these next two. We're going to set up the same x approaches infinity, y approaches whatever. That's going to look exactly the same for every problem that you do. You just have to change the y according to what the problem is doing. Okay, x approaches negative infinity. You might remember doing these in algebra. I feel like you guys are pretty good at these, or at least my algebra kids in general usually take to this pretty easy. Okay, so x to the fourth power, and he's positive x to the fourth power, and since he's got all this junk after him, he really is going to look like a W instead of a flat tire. So if he was just x to the fourth power, that's the flat tire, but he will kind of look like a W. So as my x's are going toward infinity, that's to the right, okay? X's are left and right, so toward infinity is going to the right. So as he's going to the right, well, he's traveling upward, okay? So my y coordinates are going toward infinity. The further out to the right he gets, the further up he goes. Okay, and kind of the same thing is happening when he goes to the left. So the further to the left he goes, the further up he goes. So that one's going to be toward infinity as well. All right, last one. I'm going to fill this one in. No. We got to write this out for every single one of them. Y goes toward in blank. X goes toward negative infinity. So anytime they ask for end behavior, like what's happening on the end of the thing, this is what you're going to write for each one. So left hand and right hand behaviors. X to the fifth power. So I said x to the fifth power kind of looks like x to the third with a little flat piece in him. Because he has that negative x in there, he is going to kind of have some humpy parts in him. So he'll probably do this, okay? If it was just x to the fifth power, he'd just be down and flat in the middle, okay? So as x is going toward infinity, that's going to the right. He's going down as he goes to the right. So we're going to put negative infinity here. And as he's going to the left, he's going up. So we will put positive infinity here. Now you'll notice that since this was x to the third power, x to the third power and x to the fifth power, you'll notice that my y's are going to end up in opposite directions. Like one's negative infinity, one's positive infinity. One's negative infinity, one's positive infinity. Did I do that wrong? Yes, I did. Shoot. And I don't have you guys there to yell at me. Wrong. X to the fifth power goes like this. Okay, you can quit yelling at the screen now. There you go. So this should actually be positive and this should be negative because he's going the wrong direction. So as he goes to the right, he's going up. As he goes to the left, he's going down. Okay, sorry, I fixed that. So, but even so, x to the third power, x to the fifth power, one of those will be positive, one will be negative. When it's an even power, both of them will be the same direction. So they'll both be either infinities or they'll both be negative infinities. Okay, so that is your end behavior. Let's go to the next one. All right, real zeros of a polynomial function. When you're finding a zero, or finding a solution, or finding an x-intercept, they all mean exactly the same thing. So if I find out that x equals 3, then that's a zero, that's a solution, that's an x-intercept. They mean exactly the same thing. The only difference is for like a factor, it's probably going to be written as x minus 3 in parentheses like that. They might also, as an x-intercept, write this as like 3 comma 0. So the notation is just a little bit different, but they all mean the same thing. Zero, solutions, factors, x-intercepts, they're all meaning the same thing. They'll just be written maybe in a little bit different form. Find all zeros of this function, and I went ahead and gave you the graph so you can probably kind of check what these are supposed to be. We're going to have 3 of them, so -1, 0, and 1 are the answers that I'm looking for. But on the homework, you won't have this graph there for you. So we're going to find these zeros. So when you're finding the x-intercepts of a solution, what you're going to do is you're going to plug 0 in for y. I think we did that once or a couple times this year, where x-intercepts means plug 0 in for y. So I'm putting 0 here and I'm trying to solve for x. So we look to see what we can do. And what I'm going to try to do first is I'm going to pull out a 2 and an x squared. Actually, I'm going to pull out a negative 2x squared. So that first piece is positive. Okay, I'm going to do that. So pull out a negative 2x squared just so that this first term right here now is going to be positive. So if I pull negative 2x squared out, I'll just have x squared. And it will be minus, if I pull out a negative 2x squared, x squared minus 1. That's what he will look like. Okay, so now once I have him as 2 separate pieces, he's kind of broken down already. We can take negative 2x squared and set him equal to 0, and we can set x squared minus 1 equal to 0. Okay, so negative 2x squared equal to 0. If we divide by negative 2, 0 divided by negative 2 is still just going to be 0, and 0 equals x squared. So then I have the square root, and the square root of 0 is still just 0, so x equals 0. Okay, so that's where I get this middle piece right here, so we've just solved for him. Okay, now this one, if I add 1 to the other side, I'll have 1 equals x squared. And then when I take the square root of 1, we have to be very, very careful when we do that, because not only is this 1, but it's positive and negative 1. So plus and minus the square root of 1 is just plus and minus 1. And that's why we get 2 of them here. So this guy right here is 1, and this guy right here is negative 1. And so anytime we take the square root, we have to remember plus and minus. Now, if you wanted to do that a little bit differently, you would notice that x squared minus 1 is a difference of squares, which is x minus 1, x plus 1. And if you do it that way, you will not forget the fact that there's plus and minus there, because when you set this equal to 0 and set that equal to 0, you'll get 1 positive, 1 negative. So if you want to factor him down as a difference of squares, you probably won't forget to do the plus and minus, but you know, that's just an extra step that you would have to do. Okay, so now sometimes you will have something called repeated zeros, which actually happened in this last example. So in this last example, 4 is the number of places, or the maximum number of places that this guy could cross. You can see that he kind of looks like an upside down W, or like an M. And really what could happen to this guy is that he could be instead of going down and touching, he could do that exactly. Right now he's just going down and touching this thing, and then he's going back up again. But what could happen instead is he could touch here, he could touch here, he could touch here, he could touch here, instead of this part being up here where he's only touching at one spot. So he could touch 4 places. And so we have a repeated 0 there because we really should have 4 answers instead of just 3. But the reason why that is because when we took the square root of x squared, we had, basically you can think about this as 2 of the answers are 0, right? We had 0 appearing 2 times because squared meant that there was 2 zeros, okay? Now there's not 2 1s and 2 negative ones over here because when we took the square root of 1, this was one of the answers, this is the other answer, which is accounting for 2 of them total, right? But 0, this is like positive 0 and negative 0, which are both the same numbers. So when you square, this is like 0 showing up as an answer twice. So that's called a repeated 0. And what we do is we say that that has a multiplicity of 2. So in this case, each one of these zeros, so 0 was a 0, negative 1 was an answer, and 1 was an answer. We'll call them answers instead of zeros, so it's not confusing. 0 had a multiplicity of 2 because it showed up as an answer twice. Negative 1 had a multiplicity of 1, and positive 1 had a multiplicity of 1. So if we add up all our multiplicities, 1 plus 1 plus 2, that gives me 4 as my exponent. So that's what I should have there for that. Okay. All right. I'll try to go through this kind of fast. In fact, okay, I'm going to skip to the next example because this one's kind of a little bit done for us. A little bit. They've already got the table set up there. So I'm just going to go to this next example. We're going to do it straight through all the way, and then we'll be done. So this thing right here, apply the leading coefficient test. So we already have the answer of what it should look like, but again, on your homework, you won't have this. I just gave this to you so that we can match up kind of the information that we gather going through this about the zeros and the additional points on the leading coefficient test, just to make sure it's consistent with this graph. So I'm kind of giving you the answer, but we're working a little bit backwards, but they won't give that to you on the homework assignment. Okay, so apply the leading coefficient test. This is an x to the 3rd power function, so I know that he's going to maybe look like this somehow, right? Because he's going downhill, so he's minus. So the leading coefficient test says that as x goes toward infinity, y is doing something, and as x goes toward negative infinity, y is doing something. Okay, so as x is going to the right, he's going downhill, so he's approaching negative infinity. As x is going to the left, he's approaching positive infinity. He's going uphill. So he looks like that. Find the real zeros of the polynomial function. So now they want us to factor this thing and break him down as much as we can. All right. I do not like fractions. I don't like fractions. So what I'm going to do is I'm going to multiply this entire thing through by 2, and that's going to get rid of the fraction, okay? And I'm allowed to do that because when we're finding zeros, we're setting this equal to 0. So not only am I multiplying everything on the right side by 2, but I'm going to multiply the left side by 2. But when I multiply it by 0, it's not going to do anything, right? Okay, so I'm going to multiply everything by 2, and get rid of that 9 over 2 because I don't like that 9 over 2. So 0 times 2 is still 0. I'm going to write this up at the top here. Negative 2x to the 3rd power is just negative 2, or negative 4x to the 3rd power. I should have multiplied by negative 2. Oh well, that's fine. Plus 12x squared. And then minus 9x, okay? 9 over 2 times 2 is negative 9. And then 6 times 2 is 12. So we have this going on now, and that's much nicer of a problem than what we had before. Okay, so now that I have this, I look at this, and he's a trinomial, and he kind of is like a complex trinomial because that number's in front of there. But let's do one more thing first. Let us pull an x out because each one of those has an x in it, and we can factor an x out. So we're going to do that first. And it's going to simplify our problem just a little bit more. x to the third plus 12x squared and minus 9. Not. Let me fix this. There we go. I think I have an eraser on here. This is my last video I'm doing of the night because, yeah, Layla's running a fever, so I know I won't be out of school today. So this is my last video, and it's a 11:15. So I'm tired. Sorry if I'm doing weird things, okay? All right, so complex trinomial, we're going to factor him. So we start by taking -4 times -9. Wow, there's me doing weird things again. -4 times -9, positive, that's going to be positive 36. So I'm going to start down over here, 36. And what I want to do is, as soon as I multiply this times that, I want to look at this and say, what can I multiply to get 36, but when I add them, give me 12. So some of you guys can figure this out. If you can't, I just start listing. 1 and 36, 2 and 18, 3 and 12. Yeah, 3 and 12. 4 and 9, and you're probably yelling at the screen right now because you're like, you're wasting time. It's 6 and 6, right? 6 and 6 is the combination that you want. So this guy right here, I'm going to just hang that x on for a little while, and I'm going to separate this into 4 pieces. So minus 4x squared, but instead of this being 12, he's going to be plus 6x, plus another 6x, and then minus 9. All right, and then we factor by grouping. So I'm going to group the first two, and group the second two. Okay, now this is going to look kind of funny with that x off this side there. So I'm going to do x, and then I'm going to do like a brackety thing. Okay, so this doesn't look so weird. What can I pull out of the first piece? -4x squared plus 6x. I can pull a negative 2x out, and left over is 2x minus 3. And out of the second piece, I can pull a 3, so 2x plus 3. And I have a 2x minus 3. That's what I have going on there. So in addition to this x, I also have 2x minus 3, which is the stuff that's in the parentheses, this guy here and this guy here. And then I have a negative 2x plus 3. That's what I have going on there. Okay, so now that I have my pieces, I have one piece here, and really I have another piece right there. So if he is equal to 0, I can just set each piece equal to 0. So first and foremost, x is equal to 0. Then I also have 2x minus 3 equals 0. And I have negative 2x plus 3 equals 0. Okay, and we're going to see how this guy works out. So if I add the 3 over, plus 3 plus 3, 2x equals 3, and you guys can skip steps if you like to. X equals 3 over 2, so x equals 1.5, and those are my places, right? There's that one and this one. And then if I do this again, and subtract the 3, so negative 2x equals negative 3, and then I divide by negative 2. Negative 3 over negative 2 is going to be positive, and it's going to be positive 1.5 again. So if you'll notice that, that's where that multiplicity is. 1.5 has a multiplicity of 2, and then 0 has a multiplicity of 1, which means that when I add them together, multiplicity of 2 plus multiplicity of 1 gives me a multiplicity total of 3, which was my power to start with. Okay, so find real zeros of the polynomial function. I'm going to just draw an arrow because I don't want to rewrite that. So all of this stuff down here. Those are my zeros, okay? And then plot a few additional points. So I know that he is touching 0 at 1.5, and blah, 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 okay? So I'm going to do test intervals that go from, so if I'm kind of looking at this as like a number line, numbers on the left side of 0 would be like negative infinity to 0. That's one of my test intervals, negative infinity to 0. Then I have the interval from 0 to 1.5. And then I have 1.5 and beyond, right? Like what's happening between 1.5 and beyond. I have to figure out what those are doing. So I know he's touching here at 0. He's touching here at 1.5, but I have no idea what's happening over here. So this guy right here is saying from negative infinity on the x, from all the way to the left until I get to 0. That's that interval. Then I have the interval from 0 to 1, and I want to figure out what he's doing. And then I have the from 1.5, sorry, 0 to 1.5, I have to figure out what he's doing, and then from 1.5 and beyond, all the way to the right, what's happening there. So representative x value. So then we just choose a point to plug in that's really nice. So between negative infinity and 0, I'm going to choose the point negative 1. From 0 to 1.5, I'm going to choose positive 1. And from 1.5 to infinity, let's choose 2. Okay, so then from there, it's just pretty simple. I'm going to plug those into these values up here. Okay, and I'm going to get a value of f there. Okay, so I'm going to cheat because I don't want to waste time plugging this in and make this video any longer. So if I plug negative 1 in, I can see on the graph. Well, shoot, I can't see on the graph. Poop, I might just have to plug it in for this one. Negative 2 times negative 1 to the third power plus 6 times negative 1 squared minus, I'm going to do 4.5 times negative 1. Yeah, we'll do that. Okay, so negative 1 to the third power is negative 1 times 2 is 2, or times negative 2 is 2, plus negative 1 squared is 1. Positive 1 times 6 is just 6. And then negative 4.5 minus 1 is positive 4.5. So if I add those together, 2 plus 6 is 8, plus 4.5 is 12.5. So he's all the way up at the top. Positive 12.5. So the sign there, since 12.5 is positive, my graph, excuse me, my graph is above the x-axis to the left side of 0, of 0. Yeah, to the left side of 0, he's above the x-axis, okay? Then here, in between 0 and 1.5, if I plug 1 in, I think they did that already. Yes, 1 is at 0.5. You can see that on the graph. I'm totally cheating, but whatever. 1 is at 0.5. Okay, and that one is, negative 0.5, sorry. And that sign is negative, so that means that between 0 and 1.5, he's going down below the x-axis. And then 2, if I plug 2 in, he is at negative 1, so he is also below the x-axis. So you can kind of see that he's up above, then he goes down below, and then he's down below again, which kind of makes this point right here something really fancy is happening at 1.5, which means that he's not crossing and going back up positive. He's only coming here and touching and then going back down. Does that make sense? I have 2 of the same sign right in a row, which means he's just touching and he's not going back up through. Okay, and what they mean by point on the graph is that this is the point negative 1, 12.5. This is the point positive 1, comma negative 0.5. That's what they mean by point on the graph. So using those test intervals to try to find out what's happening between those values that I found were 0, I can determine what's going on with the graph a little bit more. Okay, so there you go. They're going to have you sketch a couple graphs of functions. So just kind of do them in a similar way. Do parts 1, 2, 3, maybe even make a table. Wouldn't hurt making it kind of the same as what this one is, and then draw the graph. So that is all I have for you, and I am going to quit.